Welcome to the Drowsy Astronaut, where we explore the cosmos at a pace designed for rest, one gentle detail at a time, and tonight we visit the loneliest place in the universe. A vast region of almost perfect emptiness called the Boötes Void. This will be a peaceful journey through emptiness itself, and you can listen straight through, drift in and out, or fall asleep whenever you're ready. Knowing that we are exploring something beautiful in its simplicity, vast in its scale. There is no danger here, no threat, just the calm contemplation of empty space, of vast distances where almost nothing exists. And this emptiness can be deeply peaceful, meditative, and perfect for rest. Whether you're here to relax, to contemplate something vast and calming, or simply to let your mind wander through space, just know then you are exactly where you need to be tonight. And lastly, I would love to know where you are listening from, whether you are in bed, at work during a quiet break, somewhere comfortable and safe. Drop a comment if you're comfortable sharing, and I hope this journey helps you find the rest you seek. And without further ado, let us begin. This video will carry you through the Boötes Void, from its discovery in 1981 through its vast emptiness, across hundreds of millions of light years of nearly empty space, and we will take our time, moving slowly and explaining everything gently along the way. We will explore what voids are, how they form, what exists within them, and what it would feel like to be there, surrounded by darkness and distance, isolated in the most profound way, and yet finding peace in that isolation. So let us start with a discovery, a moment in the early 1980s, when astronomers were mapping galaxies and found something unexpected, a region where galaxies should exist but mostly do not. A hole in the cosmic web of matter that fills the universe. In 1981, astronomer Robert Kirshner and his colleagues were conducting a galaxy survey, measuring the distances to galaxies in the constellation Boötes, and they noticed something strange, a region where galaxies were mysteriously absent, as if something had carved out a vast empty space. This empty region came to be called the Boötes Void, and further observations confirmed its reality, showing that across a region 330 million light-years wide, there were only about 60 galaxies, when there should have been 2,000 or more, based on the average density of the universe. The void was not completely empty, but it was far emptier than it should be. And this discovery raised questions about how such regions form, whether they are common, and what they tell us about the structure of the universe on the largest scales. The discovery came from patient work, from systematic observation, astronomers measuring one galaxy after another, building a three-dimensional map of space, and as the map grew, the void emerged like a shadow, a region where data points were mysteriously absent. Initially, they questioned their methods, wondering if their instruments had failed, or if their distance measurements were incorrect, creating an illusion of emptiness where galaxies actually existed. But repeated observations confirmed what seemed impossible, a genuine void in the distribution of galaxies across space. The astronomical community was fascinated and puzzled in equal measure, because standard models predicted a relatively uniform distribution of galaxies, with random variations but nothing approaching the scale of emptiness they had discovered in Boötes. Some astronomers suggested the void might be filled with dark galaxies, objects too faint to detect with existing telescopes, and that better instruments would eventually reveal a normal population scattered throughout the region, filling in what appeared to be empty space. But deeper surveys with more sensitive equipment confirmed the void's reality, finding only a handful of additional faint galaxies, far too few to explain away the profound underdensity that characterized this remarkable region of space. The void became a challenge to theory, forcing astronomers to reconsider how structure forms on the largest scales, how gravity shapes the distribution of matter across billions of light years, and whether cosmic structure was more complex, more interesting than previously imagined. The Boötes Void is enormous, almost incomprehensibly large, spanning 330 million light-years from one side to the other, and to cross it at the speed of light would take more than 300 million years, a time span longer than complex life has existed on Earth. Within this vast region, there are only about 60 known galaxies, compared to the 2,000 or more that should exist in a typical region of this size, making it 97% emptier than average, one of the most underdense regions ever discovered in the universe. The void is not perfectly spherical. It is slightly irregular in shape, stretching across the sky in the constellation Boötes, and it lies about 700 million light-years from Earth, far enough that the light we see from its edges left those regions when Earth was still a very young planet. Discovering the void was surprising because astronomers had expected galaxies to be more or less uniformly distributed, but the void showed that structure exists on enormous scales, that the universe is not smooth but has vast empty regions separated by regions where galaxies cluster together in filaments and walls. Since its discovery, astronomers have found many other voids, some even larger than Boötes, and they have come to understand that voids are a natural feature of cosmic structure, as natural as the filaments and clusters, all part of the cosmic web that defines the large-scale organization of matter in the universe. But the Boötes Void remains special because it was one of the first discovered, and because it sparked questions about the universe that continue to this day, questions about dark matter, dark energy, and the processes that shape structure on the largest scales we can observe. The void's discovery changed astronomy fundamentally, revealing that our universe is organized in ways more complex than simple uniform expansion, that matter clumps and leaves gaps, creating a cosmic architecture that resembles biological structures or soap foam more than a smooth, expanding cloud of galaxies. This architecture tells a story about the early universe, about tiny fluctuations in density that existed shortly after the Big Bang, and how those microscopic variations grew over billions of years into the vast structures we observe today. Tonight we will explore this void gently, imagining what it would be like to travel through such emptiness, to exist in a galaxy within the void, and to contemplate the vast distances and profound isolation that define this loneliest place in the cosmos. Picture empty space stretching in all directions, darkness reigning supreme, and know that we will explore this emptiness together, finding beauty in the void, peace in the vastness, and understanding in the structure that creates such remarkable regions of almost nothing. Voids like Boötes are found throughout the universe, and understanding them helps us understand how structure forms, how gravity pulls matter together in some places while leaving other regions nearly empty, and how the universe has evolved from smooth uniformity after the Big Bang to the cosmic web we see today. The discovery of voids changed how astronomers think about the universe, revealing that galaxies are not scattered randomly, but organized into patterns, clustered along filaments and walls, with vast voids between them. And this pattern tells us about the forces and processes that shaped the cosmos over billions of years. The Boötes Void is lonely not because it is hostile, but because it is empty. There are few galaxies, little light, and vast distances between anything that does exist. And this emptiness creates a kind of isolation that is profound, a loneliness on cosmic scales that we can barely comprehend. But this loneliness is also peaceful. There is no crowding, no collisions, just vast, empty space where darkness reigns and distance stretches beyond imagination. And contemplating this can be calming, meditative, and perfect for rest, letting the mind drift through emptiness without distraction or concern. As you prepare to sleep, let the concept of the void settle. Imagine vast, empty space, peaceful and dark, and know that this emptiness exists far away, a natural part of the universe, and that exploring it in imagination is safe, calming, and a journey into one of nature's most serene creations, waiting to be understood. The void invites contemplation, invites us to slow down, to consider what it means for space to be truly empty, and in this consideration, we find a kind of peace that comes from understanding vastness, from accepting that emptiness is as natural as fullness, as essential to cosmic structure as the galaxies themselves. Let us explore the scale of the Boötes Void, understanding just how empty it truly is, and comparing it to normal regions of space so we can appreciate the profound lack of matter that defines this remarkable region. The void spans 330 million light-years across, and to put this distance in perspective, our entire Milky Way galaxy is only 100,000 light-years wide, meaning you could fit more than 3,000 Milky Ways side by side across the void's diameter. The distance from our galaxy to Andromeda, our nearest large neighbor, is 2.5 million light-years, and even this vast gulf is tiny compared to the void. You could fit 130 Andromeda-sized gaps across the void, and still the numbers feel inadequate to capture the true scale. Light from one side of the void takes 330 million years to reach the other side. And during that time on Earth, life evolved from simple organisms to complex animals, continents drifted, mountains rose and eroded, and entire species came and went, all in the time light crosses the void. To comprehend this scale requires thinking beyond human experience, beyond even geological time on Earth, into cosmic timescales where millions of years are brief moments, and where distances become so vast that conventional understanding breaks down, leaving only mathematics and imagination. If you could somehow travel at the speed of light, starting from one edge of the void and heading toward the other, you would spend more than 300 million years crossing mostly empty space, seeing almost nothing for vast stretches of time, with only occasional faint galaxies marking your progress through the darkness. During your journey, if you could look back at Earth, you would see its history unfolding in reverse, complex life disappearing, oceans forming, the planet cooling from its molten state. All while you traveled through cosmic emptiness, surrounded by darkness and profound distance. The scale makes even galaxies seem insignificant, because a galaxy containing hundreds of billions of stars is just a tiny speck in the void's vastness. And the distances between these specks are so enormous that even galaxy-scale objects become lost, invisible in the immensity. In a typical region of space this size, you would expect about 2,000 galaxies, each one containing billions or even trillions of stars, and these galaxies would be scattered throughout the volume, creating a rich tapestry of light and matter distributed across the three-dimensional space. But in the Boötes Void, there are only about 60 galaxies, less than 3% of what should be there, and these few galaxies are scattered so far apart that the average distance between them is tens of millions of light years, far greater than the spacing in normal regions. This emptiness is hard to visualize because we live in a relatively crowded part of the universe. Our Milky Way is part of a small group of galaxies, and we can see other galaxies in the sky, but in the void, the sky would be almost completely dark, with only a handful of faint smudges representing distant galaxies. The void is not completely empty. It contains dark matter and gas, but the normal matter that makes stars and galaxies is scarce, and the few galaxies that do exist are mostly small, dwarf galaxies with far fewer stars than typical galaxies like our Milky Way. Imagine standing on a planet in a galaxy within the void, looking up at the night sky and seeing almost nothing. No Milky Way band, no nearby galaxies, just a handful of faint spots scattered across the darkness. And the cosmic microwave background, a faint uniform glow from the Big Bang, barely detectable even with instruments. The isolation would be profound, not just physical but visual, because light from other galaxies would take tens of millions of years to reach you, and the universe would seem empty, almost barren, as if you lived in a region where creation had forgotten to place much matter. This emptiness is natural, a result of how gravity works on large scales, pulling matter toward dense regions and leaving voids behind. And the Boötes Void is simply one of the largest and most prominent examples of this natural process, a region where matter was pulled away rather than concentrated. The scale of the void reminds us how vast the universe is, how much empty space exists between the islands of matter, and how rare and precious matter actually is, concentrated in galaxies and clusters, while vast regions remain nearly devoid of anything at all. To put the void's emptiness in another perspective, if the universe were represented as an ocean, normal space would be water with islands of matter, but the void would be a vast air bubble, a region where the water itself is mostly absent, leaving almost nothing but empty space. The void contains perhaps 1% of the matter it should have, meaning 99% of what we expect is simply not there, pulled away by gravity over billions of years, flowing toward denser regions and leaving behind this remarkable emptiness that challenges our intuitions. The void is not expanding in the sense of growing from some internal process, but it is growing because the universe itself is expanding, space itself stretching, and this expansion pulls galaxies apart, making the void even larger over cosmic time, increasing the already profound emptiness. In billions of years, the few galaxies in the void will be even farther apart, separated by even greater distances, and the void will become more empty, more isolated, and the loneliness will deepen as the universe's expansion accelerates under the influence of dark energy, pulling everything apart. This future emptiness is the fate of much of the universe. As expansion continues, voids will grow, and eventually, most regions of space will be as empty as the Boötes Void is now, with galaxies isolated in vast dark expanses, unable to see or reach their neighbors. But for now, the Boötes Void is unusual, a region more empty than most, and studying it helps astronomers understand how structure forms, how voids develop, and what the future holds for the universe as expansion continues to pull matter apart across cosmic time. The void challenges our sense of what is normal in the universe, because we naturally think of space as containing stars and galaxies, but the void shows us that emptiness is actually more common, that most of space is empty, and that the galaxies we see are rare concentrations in an otherwise vacant cosmos. This perspective shift is profound, realizing that we live in an unusually rich region, that our view of a galaxy-filled universe is not typical, and that vast expanses of nearly empty space are the norm rather than the exception in cosmic architecture. The scale invites meditation on vastness itself, on what it means for distances to be so enormous that even light takes hundreds of millions of years to cross them, and on how small we are, how local our experience compared to the immensity of cosmic structures like the void. Understanding these scales helps us appreciate both the universe's vastness and our own existence within it, finding peace in the knowledge that such enormous empty regions exist, that the cosmos has room, vast room, for emptiness to coexist with the pockets of matter and life we call home. To understand the Boötes Void, we need to understand how voids form in general, and this requires thinking about the early universe, about tiny fluctuations in density that grew over billions of years into the cosmic web we see today. In the very early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density, regions that were slightly denser and regions that were slightly less dense. And these tiny differences were the seeds of all structure that would come later. Gravity amplified these tiny fluctuations over time, pulling matter toward the denser regions and away from the less dense regions. And this process, acting over billions of years, created the cosmic web, a vast network of filaments, walls, and voids that defines the large-scale structure of the universe. The denser regions became filaments and clusters where galaxies formed, and the less dense regions became voids, spaces where matter was pulled away toward the surrounding dense regions, leaving behind vast empty spaces dotted with only a few galaxies that formed from the small amounts of matter that remained. These fluctuations in the early universe were incredibly small, variations of only 1 part in 100,000 in the density of matter, yet these tiny differences were enough, given billions of years, for gravity to work its slow transformation, turning microscopic variations into cosmic structures. The process began when the universe was only 380,000 years old, when matter first decoupled from radiation and gravity could begin pulling it into clumps, and from that moment forward, structure grew steadily, with denser regions attracting more matter and less dense regions losing what little they had. Dark matter plays a crucial role in this process because it makes up most of the matter in the universe, and its gravity drives the formation of structure, pulling normal matter along with it and creating the scaffolding on which galaxies form. In regions that became voids, dark matter was also sparse, pulled away toward denser regions, and without dark matter's gravity to hold it, normal matter followed, flowing along invisible paths toward the filaments and clusters, leaving the void regions with very little matter of any kind. The process is gradual, taking billions of years, and it is still continuing today, matter still flowing from voids toward denser regions, though the process has slowed as the universe's expansion has accelerated under the influence of dark energy, which works against gravity's pull. Voids are natural consequences of how gravity works. They are not holes punched into the universe, but regions where matter was never concentrated, regions where the initial density fluctuations were slightly negative, leading gravity to pull matter away rather than pulling it together. The Boötes Void formed this way, starting from a region with slightly lower density, and over billions of years, matter flowed out toward the surrounding filaments, leaving behind the vast empty region we observe today, with only a few galaxies that formed from the small amount of matter that remained. Computer simulations of structure formation reproduce voids like Boötes naturally, showing that they are expected features of a universe governed by gravity and dark matter, and these simulations match observations remarkably well, confirming our understanding of how large-scale structure develops over cosmic time. The cosmic web of filaments, walls, and voids is beautiful in its structure, resembling foam or a sponge, with matter concentrated along thin filaments and walls, and voids filling most of the volume. And this structure reveals the interplay of gravity, dark matter, and dark energy shaping the universe. Understanding voids helps us understand this structure. Because they are as important as the dense regions, they define the spaces between structure, and studying them tells us about the forces and processes that have shaped the universe over 13.8 billion years. Imagine watching this formation process in time-lapse, starting with the early universe where matter is nearly uniform, then watching as tiny seeds of structure grow. As matter flows along invisible channels toward denser regions, and voids emerge like bubbles, growing larger as matter drains away. The process resembles water draining from a sponge, with matter flowing downhill in gravitational potential, following paths of least resistance toward the deepest gravitational wells, and leaving behind empty spaces where once there was a more uniform distribution. Voids grow over time as the universe expands, the distances within them increase, and the few galaxies they contain move farther apart, and eventually, billions of years from now, many voids will be even emptier than they are today, with their galaxies isolated beyond any hope of contact. This evolution of voids is part of the universe's long-term fate. As dark energy drives accelerating expansion, voids will dominate more and more of space, and the universe will become increasingly empty, with galaxies isolated in vast dark regions unable to see or reach others. But for now, voids like Boötes are relatively unusual. They are emptier than average, and most of space still has some galaxies, some structure, and voids stand out as particularly underdense regions rather than being the norm they will eventually become. So voids are windows into the future, showing us what much of the universe will eventually look like, and studying them helps us understand where the cosmos is heading, what structure will look like billions of years from now when expansion has pulled everything even farther apart. The formation of voids also tells us about dark energy's role, because dark energy opposes gravity, preventing matter from collapsing further and allowing voids to grow as expansion accelerates. And measuring void properties helps astronomers understand dark energy's strength and how it affects cosmic evolution. Dark energy was negligible in the early universe when matter density was high. But as the universe expanded and matter became more dilute, dark energy's influence grew, and now it dominates the universe's evolution, driving accelerating expansion and ensuring that voids will continue growing indefinitely into the future. Understanding how voids form requires understanding this entire cosmic history, from the Big Bang through the formation of structure to the present day and beyond, and each void we observe is a record of this history, a testament to billions of years of gravitational evolution and cosmic expansion. The process creates beauty from simplicity, starting with tiny random fluctuations, and through the patient action of gravity over billions of years, creating the magnificent cosmic web, a structure so vast and intricate that it contains within it both the densest galaxy clusters and the emptiest voids like Boötes, all part of one continuous pattern. The Boötes Void is not completely empty. It contains about 60 known galaxies, scattered across its vast volume, and these galaxies are special, isolated and lonely, evolving differently from galaxies in denser regions, shaped by their profound isolation from neighbors. These galaxies are mostly small, dwarf galaxies with far fewer stars, perhaps millions or billions rather than the hundreds of billions typical of large galaxies, and they are faint, difficult to detect, scattered tens of millions of light-years apart across the void's dark expanse. The galaxies in the void are lonely in the truest sense. They have few, if any, nearby neighbors, no galaxy groups or clusters, just isolation, and this loneliness affects how they evolve, how they form stars, and what they look like compared to galaxies in richer environments. In dense regions of the universe, galaxies interact frequently, merging with neighbors, passing close enough to trigger star formation and feeling the gravitational influence of nearby galaxies. But in the void, such interactions are rare, and galaxies evolve in relative isolation, quietly and slowly. This isolation means void galaxies form stars more slowly, because interactions that trigger star formation bursts are absent, and they grow more slowly, accumulating mass at a leisurely pace without the dramatic events that characterize galaxies in clusters. Void galaxies are often bluer than average, indicating they have younger stars, and this seems paradoxical given their isolation. But it may be that without interactions to strip away gas, void galaxies retain their fuel for star formation longer, allowing them to continue forming stars at a steady, slow rate for extended periods. The exact properties of void galaxies are still being studied because they are faint and far away, difficult to observe in detail, but what we know suggests they are different from typical galaxies, shaped by their unique environment of profound emptiness and isolation. If you could visit a void galaxy, you would find it quiet. Few supernovae, little activity, just stars forming slowly and aging gradually, and the night sky from a planet there would be almost empty, showing only the stars of your own galaxy and perhaps one or two faint smudges representing the nearest void galaxies, tens of millions of light-years distant. The loneliness of a void galaxy would be profound on a cosmic scale. No nearby companions, no interactions, just isolation in a vast, dark space, and any civilization there would grow up thinking the universe was mostly empty, that galaxies were rare, and that their own galaxy was perhaps unique or nearly so. Discovering the cosmic web from within a void would be difficult, because most of the structure would be far away, beyond the void's edges, and telescopes would need to be powerful to see the distant filaments and clusters that define the universe's large-scale organization. Such a civilization might develop a very different cosmology, believing the universe was emptier than it actually is, and only with advanced telescopes and surveys would they discover that their isolation is unusual, that beyond their void lies a universe rich with galaxies and structure. This thought experiment reminds us how much our perspective shapes our understanding, how location matters, and how lucky we are to live in a relatively crowded region where we can see many galaxies and piece together the universe's structure without facing the challenges of void isolation. The 60 galaxies in the Boötes Void are scattered across its volume, with typical separations of tens of millions of light-years. And exploring this distribution helps astronomers understand whether voids are truly empty or just underdense, whether they evolve over time. Some studies suggest there may be more galaxies in the void than currently known, very faint ones that have not yet been detected, and future surveys with more sensitive instruments may reveal additional members. increasing the galaxy count but still leaving the void dramatically underdense compared to normal regions. Even if more galaxies are found, the void will remain remarkably empty, because even 100 galaxies scattered across such a vast volume would represent less than 5% of the expected number, and the fundamental nature of the void as a region of profound underdensity would remain unchanged. So the void's galaxies are rare, isolated, and lonely, shaped by their environment, evolving differently from typical galaxies, and offering astronomers a unique laboratory for studying how galaxies behave when freed from the crowding and interactions that characterize denser environments. Each void galaxy has its own story, its own history of star formation, perhaps beginning billions of years ago when the void was less empty, and continuing today in isolation, slowly converting gas into stars, creating stellar generations that will never see the rich galaxy clusters that dominate normal space. Some void galaxies may have formed early when the void was not yet evacuated, when more matter remained in the region, and these galaxies would have witnessed the gradual emptying of their neighborhood, watching as other galaxies drifted away or were pulled toward denser regions, leaving them increasingly isolated. Other void galaxies may be younger, forming from the sparse gas that remained, after most matter had been pulled away, and these late-forming galaxies would have grown up in already empty space, never knowing a time when their surroundings were richer, when neighbors were closer or more numerous. The variety among void galaxies reflects the complexity of their formation histories. Some may have fallen into the void from denser regions, captured by the void's gravitational influence, while others formed in place, coalescing from the meager amounts of matter that gravity could not pull away entirely. Studying these individual galaxies requires patience and powerful telescopes, because each one is faint and distant, requiring long exposures to detect and study, but each observation adds to our understanding, revealing how isolation shapes galactic evolution and what properties are fundamental versus environmentally determined. The colors of void galaxies tell stories about their star formation. Blue galaxies are actively forming stars, while redder galaxies have older stellar populations, and the mix of colors in the void provides clues about how star formation proceeds in such isolated conditions. Some void galaxies show signs of past interactions despite their current isolation, distorted shapes or tidal features that suggest they once had companions, galaxies that either merged with them or passed close enough to leave gravitational scars before drifting away into the darkness. These clues hint at a more dynamic past for the void, when it contained more galaxies, when interactions were more common, and the current isolation represents an evolved state, the result of billions of years of gravitational drainage that left only the sparse population we observe today. The void galaxies stand as monuments to isolation, each one a reminder that loneliness on cosmic scales means evolving without influence, changing slowly, aging quietly, and existing in a region where the nearest neighbors are so distant that interaction is impossible, leaving each galaxy to follow its own solitary path through time. Imagine embarking on a journey through the Boötes Void, starting at one edge and traveling toward the other side, crossing 330 million light-years of nearly empty space, and we will follow this imaginary journey together, experiencing the profound emptiness at a pace designed for rest and contemplation. We begin at the void's edge, standing at the boundary between normal space and the void, looking outward toward the galaxies we are leaving behind, rich clusters and filaments visible in many directions, and then turning to face the void, seeing the darkness ahead, the sparse scattering of faint galaxies that mark our path across this lonely region. We start moving into the void, traveling at the speed of light for this thought experiment. And even at this impossible speed, our journey will take more than 300 million years, longer than complex life has existed on Earth, and we settle in for this long voyage across emptiness. At first, the change is gradual. Galaxies behind us remain visible, receding slowly, but ahead the darkness deepens, and the few galaxies within the void come into view, faint smudges separated by vast distances. And we realize we are entering a realm fundamentally different from the rich neighborhood we left behind. Days pass at light speed, then weeks, and galaxies behind us grow fainter, becoming harder to see. And ahead, the void stretches endlessly, dark and empty, and we see our first void galaxy, a small dwarf, faint and blue, isolated in the darkness, and we pass it, continuing deeper. Millions of years pass in our journey, and we cross vast empty regions, seeing nothing, just darkness in all directions, and occasionally another void galaxy appears, each one separated from the last by tens of millions of light years, brief islands of light in an ocean of emptiness. The isolation becomes profound. We are far from any dense region now, surrounded by emptiness in every direction, and the few galaxies we see are scattered, lonely, and the darkness between them is complete. No stars, no nebulae, just empty space stretching endlessly. This is the heart of the void, the loneliest place, where distances between anything are so vast that even light takes millions of years to cross them, and where the universe seems empty, almost barren, as if matter is a rare exception rather than the norm. Continuing forward, we pass more void galaxies, each one isolated, each one quiet, and we realize that if any civilization existed in these galaxies, they would grow up thinking the universe was empty, that their galaxy was perhaps alone, and discovering other galaxies would require powerful telescopes and patient surveys. The journey continues, tens of millions of years passing, and the void seems endless, unchanging, just darkness and occasional faint galaxies, and we begin to understand the scale, the profound vastness of this empty region, and how insignificant even galaxies seem when scattered so thinly across such enormous volumes. We have crossed perhaps a quarter of the void now, 80 million years into our journey, and looking back, we can barely see the galaxies we left behind, and looking forward we see more darkness, more empty space, with only a handful of faint void galaxies marking our progress through this cosmic desert. The emptiness becomes meditative after a while, the unchanging darkness creating a kind of peace, because there is nothing to distract, nothing to worry about, just the slow passage of cosmic time and the vast distances. And in this emptiness we find a strange comfort, a simplicity that comes from traveling through nothing. Halfway through the void now, 165 million years into our journey, we have seen perhaps 20 void galaxies, each one a brief moment of light in the darkness, and between them, nothing. Just empty space, stretching for tens of millions of light years in every direction, a testament to the void's profound underdensity. The sense of isolation is complete now. We are truly in the middle of nowhere, surrounded by emptiness on all sides, and the nearest significant structures are hundreds of millions of light years away, far beyond our ability to see. And we understand what it means to be truly alone in the cosmos. If we stopped here, floating in the void's heart, we would see almost nothing. Perhaps one or two faint galaxies scattered across the sky and the cosmic microwave background glowing faintly, but otherwise just darkness, pure and complete, the deepest isolation imaginable on any scale. Time loses meaning in such emptiness because nothing changes. The darkness remains constant, the silence absolute, and only our continued motion provides any sense of progress. But even that feels uncertain, as if we are standing still while the universe remains frozen around us. Eventually, after more than 300 million years of travel, we approach the far edge of the void, and galaxies ahead become more numerous, denser regions coming into view, and we realize we are leaving the void, crossing back into normal space where structure is richer. Looking back, the void is a vast dark region behind us, almost invisible except for its few scattered galaxies, and we appreciate what we crossed, a region where emptiness reigns, where loneliness is measured in millions of light years, and where the universe shows us its capacity for creating vast spaces nearly devoid of matter. This imaginary journey helps us understand the void's scale, how long it would take to cross, how empty it truly is, and what it would feel like to travel through such a region, seeing almost nothing for millions of years, experiencing isolation on cosmic scales. Of course, no one will ever make this journey. The distances are too vast, the timescales too long, but imagining it helps us appreciate the void, understand its emptiness, and see it not as an abstract concept, but as a real place, a region of space with properties we can contemplate and visualize. The journey also reminds us how fortunate we are to live where we do, in a relatively rich region where galaxies are abundant, where we can see structure, and where the universe seems full of matter rather than empty, giving us a perspective very different from what a void civilization would have. Crossing the void in imagination leaves us changed, more aware of scale, more appreciative of distance, and more understanding of what emptiness truly means, not as an absence that frightens, but as a natural state of space, a canvas on which matter occasionally gathers to create islands of light and structure. The journey teaches patience because even at light speed, progress seems slow, and teaches humility because even galaxies seem small and insignificant when scattered across such vastness, and teaches perspective because understanding such emptiness helps us appreciate the richness of our own cosmic neighborhood and the rarity of matter itself. Let us contemplate what it would feel like to exist in the void, to float in empty space far from any galaxy, surrounded by darkness, and experiencing the profound silence and isolation that defines this loneliest place in the universe. In the void, far from any galaxy, you would see almost nothing. No nearby stars, no glowing gas, no bright nebulae, just darkness in every direction, with perhaps one or two faint smudges marking distant void galaxies, millions of light years away. The cosmic microwave background would surround you, a faint uniform glow from the Big Bang, but it is so faint, requiring sensitive instruments to detect, and to your eyes the universe would simply appear dark, empty, as if you floated in an infinite black void with no reference points. This emptiness would be profound, not scary, but peaceful in its totality. No light pollution, no nearby objects, just the purest darkness imaginable. And in this darkness, you could truly appreciate the concept of nothing, of space without content, stretching endlessly in all directions. The silence would be equally profound, though space carries no sound. The metaphorical silence of having nothing nearby, no gravitational interactions, no light from nearby sources, just you floating in emptiness, with the universe's faint background glow the only sign that you exist in a cosmos at all. Time would pass differently in the void, not physically but psychologically, with no nearby events to mark its passage, no stars going supernova, no galaxies merging, just empty space stretching through billions of years, essentially unchanged. And this changelessness creates a kind of timelessness. If you waited in the void for millions of years, very little would change around you. The faint galaxies might shift slightly due to the universe's expansion, but otherwise your surroundings would remain constant, dark and empty, as if time had stopped or become meaningless in this region. This timeless quality is part of what makes voids peaceful to contemplate. They are places where change is slow, where the universe's frantic activity seems distant, and where emptiness reigns supreme, offering a kind of cosmic calm found nowhere else in the universe. Floating in the void, you might see the universe's expansion more directly, watching the few galaxies visible slowly receding, pulled apart by dark energy, and over millions of years, you would witness the void growing larger, emptier, more isolated as expansion accelerates and pulls everything farther from everything else. This expansion is gentle, imperceptible on human timescales, but over cosmic time, it transforms the universe. And in the void where galaxies are already sparse, the effect would be more noticeable, as the few islands of light drift farther apart, increasing the already profound isolation. The void would teach you patience, because nothing happens quickly there. Processes that take millions of years are the norm, and change, when it comes, is so gradual as to be almost invisible, creating a realm where the universe's evolution proceeds at its slowest pace. And yet despite this slowness, this emptiness, this silence, the void is beautiful in its simplicity. It shows us that not everything needs to be filled, that emptiness has its own kind of presence, and that darkness and distance can create peace rather than fear. The experience of floating in such emptiness would be transformative, stripping away all distractions, all complications, leaving only the pure experience of existing in space. And in that purity you might find a kind of meditation, a connection to the fundamental nature of the cosmos that is impossible to achieve in richer, more crowded regions. You would become aware of your own existence more acutely, because in the void there is nothing else to be aware of, just yourself and the darkness, and this awareness might lead to profound insights about consciousness, about being, about what it means to exist in a universe that is mostly empty space. From a planet in a void galaxy, the night sky would be remarkably empty, showing only the stars of your own galaxy and perhaps one or two faint neighboring galaxies. And the Milky Way band we see from Earth would be your own galaxy's disk, but beyond that, almost nothing, just darkness stretching in all directions. Astronomers on such a world would have difficulty discovering the cosmic web, because most of it would be far away, beyond the void's edges, and they would need very powerful telescopes to detect the distant filaments and clusters that define the universe's structure. They might initially believe their galaxy was alone, or nearly so, and discovering that the universe is actually full of galaxies, but they just happen to live in an unusually empty region, would be a profound revelation, changing their entire cosmic perspective. This thought experiment shows us how location shapes understanding, how living in the void would create a very different view of the universe, and how fortunate we are to live in a region rich enough to reveal cosmic structure relatively easily. The inhabitants of a void galaxy might develop a philosophy centered on isolation, on the beauty of emptiness, on the rarity of matter and structure, and when they finally discovered the cosmic web, their response might be wonder at the richness beyond their void, or perhaps sadness at what they had missed growing up in such emptiness. Or they might feel grateful for their isolation, for the peace it brings, for the simplicity of a universe that seems empty, and they might view the crowded regions of space as chaotic, as too busy, too complicated, preferring their own quiet corner of the cosmos where emptiness reigns and silence is complete. The void's silence is not absence but presence, a quality that fills the space, making it something to experience rather than something lacking. And in this silence, you might hear yourself more clearly, understand your thoughts, feel your existence in ways impossible when surrounded by noise and distraction and the busy activity of normal space. Contemplating this silence as you drift towards sleep brings its own kind of peace, imagining the vastness, the darkness, the complete absence of distraction, and finding in that imagined emptiness a reflection of the peace we seek when we close our eyes, when we let go of the day's concerns and drift into the quiet darkness of rest. The Boötes Void is not unique. It is simply one of the most prominent examples, and astronomers have discovered many other voids throughout the universe, some even larger, all of them regions where galaxies are scarce and emptiness dominates across vast scales. Voids are actually quite common in the cosmic web. They make up most of the universe's volume, with galaxies concentrated along thin filaments and walls, and the spaces between these structures are voids, regions where matter was pulled away by gravity over billions of years. Some voids are smaller than Boötes, only a few 100 million light-years across, and some are larger, stretching across billions of light-years, and together they form a network of empty regions that defines the large-scale structure of the universe alongside the filaments and clusters. One nearby void is the local void, which lies in the direction of Virgo, only about 150 million light-years from us, and it is smaller than Boötes, but still remarkably empty, containing very few galaxies across its extent. The local void affects our own motion through space because its underdensity creates a gravitational push away from it, and combined with the gravitational pull of nearby clusters, this shapes the Milky Way's velocity relative to the cosmic microwave background, causing us to move in a specific direction through space. Discovering voids has helped astronomers understand the cosmic web's structure, showing that matter is organized hierarchically, with galaxies in groups, groups in clusters, clusters along filaments, and voids filling the spaces between, creating a foam-like pattern that extends across the entire observable universe. Some voids are truly enormous, like the Eridanus supervoid, which is about 1 billion light-years across, one of the largest structures known, and its existence pushes the limits of what structure formation models predict, raising questions about how such massive voids form. The Eridanus supervoid is particularly interesting because it is associated with a cold spot, a region in the cosmic microwave background that is slightly cooler than average, and some scientists think the void's gravity might affect the background radiation, creating this anomaly, though this connection is still debated. Voids vary in their properties. Some are rounder, some more elongated. Some contain very few galaxies, others have slightly more. And studying this variety helps astronomers understand how voids form, how they evolve, and what they tell us about the forces shaping the universe. Computer simulations of structure formation naturally produce voids, showing that they are expected features in a universe governed by gravity and dark matter. and the simulated voids match observations reasonably well, confirming our understanding of how large-scale structure develops over cosmic time. The distribution of void sizes and shapes provides a test of cosmological models, because different amounts of dark matter and dark energy would produce different void properties, and by measuring real voids and comparing them to simulations, astronomers can constrain the parameters that govern the universe's evolution and structure. Voids are not just empty space, they are tools for understanding cosmology, and each void discovered adds to our knowledge of how the universe is organized, how it got that way, and where it is heading as expansion continues to pull matter apart over the coming billions of years. Some astronomers study voids specifically, conducting surveys to find them, measuring their sizes, their galaxy content, and their distribution. And this work has revealed that voids are a fundamental part of cosmic structure, as important as clusters and filaments for understanding how the universe is organized. The discovery that much of the universe is void rather than filled was surprising when first realized, because earlier assumptions had been that galaxies were more uniformly distributed, but voids showed that structure is highly non-uniform, with most volume being empty and matter concentrated in relatively small regions along filaments. This structure resembles biological structures like neurons or soap bubbles, with matter concentrated along thin boundaries and vast empty spaces between. And this resemblance is not coincidental. It reflects how systems organize when shaped by forces like gravity or surface tension that create networks of dense regions and voids. Understanding voids helps us understand this broader pattern, the cosmic web that defines the universe's architecture, and by studying the emptiest regions, we learn about the processes that created the densest regions. Because the two are linked, two sides of the same structure formation process. The catalogue of known voids grows with each new galaxy survey, revealing more empty regions, measuring their properties more precisely, and showing us that voids exist at all scales, from small voids a few tens of millions of light years across to supervoids that span billions of light years. Each void has its own character, its own history. Some formed early in cosmic history when structure was just beginning to emerge, while others are younger, still in the process of being evacuated as matter continues flowing toward denser regions. And studying this diversity reveals how void evolution proceeds over cosmic time. Some voids are connected, forming chains of empty regions, like bubbles in foam that share walls, and these connections show how the cosmic web structure is truly three-dimensional, with voids and filaments weaving together in complex patterns that extend throughout space. The Great Void is another massive example, discovered through patient galaxy surveys, showing a region where galaxies are dramatically underdense, and like Boötes, it challenges our understanding, forcing us to refine our models, and teaching us about the limits of structure formation in a universe shaped by gravity and dark energy. Mapping all these voids creates a picture of the universe's skeleton, the underlying structure on which galaxies are draped, and this picture shows us that emptiness is the norm, that voids occupy most of space, while galaxies cling to the thin filaments and walls that separate these vast empty regions. This perspective transforms our understanding, revealing that we think of the universe backward. We see galaxies and think they fill space, but actually they occupy only a tiny fraction, clinging to the edges of voids. And the voids themselves, the empty regions, are what truly dominate the cosmos on the largest scales. Voids matter to astronomers because they provide unique insights into cosmology, into dark matter, dark energy, and the forces that shape the universe on the largest scales, and studying voids helps us test theories and understand the cosmos more deeply. The size and number of voids depend on cosmological parameters, on how much dark matter exists, how strong dark energy is, and how structure formed in the early universe, and by measuring void properties and comparing them to predictions, astronomers can constrain these parameters and refine their models. Voids are sensitive to dark energy in particular, because dark energy affects how structure grows, and more dark energy means structure grows more slowly and voids grow larger, so measuring voids tells us about dark energy's strength and how it has influenced cosmic evolution. Dark energy is the mysterious force causing the universe's expansion to accelerate, and understanding it is one of the biggest challenges in cosmology, and voids provide one way to study it, complementing other methods like supernova observations and cosmic microwave background measurements. The fact that voids exist at all tells us something important, that the early universe had density fluctuations, regions slightly denser and slightly less dense, and these fluctuations were the seeds of all structure, growing over time into the cosmic web we observe today. If the early universe had been perfectly uniform, with no fluctuations, no structure would form, no galaxies, no voids, just a smooth distribution of matter forever. And the fact that we see structure, including voids, tells us the early universe had these crucial fluctuations. These fluctuations are imprinted in the cosmic microwave background, visible as tiny temperature variations across the sky, and they match the fluctuations needed to produce the cosmic web, confirming that structure grew from these early seeds over billions of years through gravitational collapse. Voids are the negative side of this process, regions where fluctuations were negative, where density was slightly lower, and where gravity pulled matter away rather than concentrating it. And understanding voids means understanding this entire process of structure formation from beginning to present. Voids also help us understand galaxy evolution, because void galaxies evolve differently from galaxies in dense regions, and comparing them tells us how environment affects galaxy properties, how interactions shape galaxies, and what happens when galaxies evolve in isolation versus in crowded neighborhoods. Galaxies in dense regions experience more interactions, more mergers, and these events trigger star formation, transform spiral galaxies into ellipticals, and shape the galaxy population, while void galaxies, isolated and undisturbed, evolve more slowly and retain properties that galaxies in clusters have lost through interactions. Studying void galaxies is like studying a control group, seeing what happens when interactions are absent, and this comparison helps astronomers understand which galaxy properties are intrinsic, which are shaped by environment, and how the cosmic web's structure influences the galaxies embedded within it. So voids are not just empty space, they are laboratories, places where conditions differ from normal regions, and studying them provides insights we cannot get from dense regions alone, making them valuable despite or perhaps because of their emptiness. The distribution of voids across the universe tests our cosmological models, because the number of voids, their sizes, and their properties depend on the fundamental parameters that govern cosmic evolution, and measuring these properties precisely allows astronomers to determine whether our models are correct or need refinement. If voids were more numerous or larger than predicted, this would suggest dark energy is stronger than we think, or that dark matter behaves differently than our models assume, and such discrepancies would force us to revise our understanding of the universe's composition and evolution. So far, the voids we observe match predictions reasonably well, confirming our basic understanding of cosmology, but small discrepancies remain, and studying voids more precisely may reveal subtle effects that help us understand dark energy's nature, dark matter's properties, or other aspects of fundamental physics. The future of cosmology involves studying voids more carefully, mapping them in detail, measuring their properties precisely, and using this information to constrain dark energy, test gravity theories, and understand cosmic structure more completely than current observations allow. Future surveys will find more voids, measure them better, and discover how they evolve over time by comparing voids at different distances, which means different cosmic ages. And this evolution tells us how dark energy and expansion have affected structure over the universe's history. Voids are becoming increasingly important in cosmology. No longer just interesting features, but tools for understanding fundamental physics. And as observational techniques improve, voids will provide some of the best tests of our theories about the universe's composition and fate. So the Boötes Void and its cousins matter deeply. They are not just empty regions to be ignored, but crucial parts of cosmic structure that teach us about the forces shaping the universe. And studying them helps us answer the biggest questions about what the cosmos is made of and where it is going. Voids also tell us about the universe's geometry and curvature because their shapes and distribution depend on whether space is flat, curved, or saddle-shaped, and measuring void properties helps astronomers determine the universe's overall geometry, one of the fundamental questions in cosmology. The emptiness of voids makes them sensitive to subtle effects, because without the complications of dense matter, dark energy's influence is more apparent, and measurements in voids can reveal details about dark energy's strength and evolution that are harder to detect in regions where matter dominates. Understanding why voids matter transforms them from curiosities into essential objects of study. From empty regions we might ignore into valuable laboratories where the universe reveals its secrets, and this transformation reflects how science progresses, finding importance in unexpected places and learning that even emptiness has much to teach us. The Boötes Void will not remain as it is forever. The universe is changing, expanding, and evolving, and the void's future depends on how expansion continues, how dark energy behaves, and what happens to the few galaxies that currently inhabit this lonely region. The universe's expansion is accelerating, driven by dark energy, and this acceleration means that galaxies are moving apart faster and faster, and the distances between them are growing, and this affects voids by making them larger, emptier, and more isolated as time goes on. In the void, where galaxies are already sparse, expansion's effect is dramatic. The few galaxies there are being pulled farther apart, and in billions of years they will be separated by even greater distances, making the void even emptier, even lonelier, as cosmic evolution continues. Eventually, perhaps hundreds of billions of years from now, the void galaxies will be so far apart that light from one will never reach another, each galaxy isolated beyond the cosmic horizon, unable to see or communicate with any neighbors, creating islands of existence in an ocean of unreachable emptiness. This future isolation is not unique to void galaxies. It will eventually affect all galaxies as the universe's expansion continues, but void galaxies will experience it first, because they are already isolated, already far from neighbors, and expansion simply increases the distances that are already profound. The void itself will grow larger as space expands, its diameter increasing, and if we could watch it over billions of years, we would see the sparse galaxies within it drift farther apart, the void swelling like a bubble, becoming an even larger region of emptiness within the cosmic web. Some models predict that eventually, trillions of years from now, the entire universe will resemble today's voids, with galaxies isolated by such vast distances that each one exists alone, unable to see others, and the night sky from any galaxy will be almost completely empty, showing only the stars of that galaxy itself. This far future is sometimes called the Big Rip or the Heat Death, depending on the details, but the common theme is increasing isolation, increasing emptiness, and the universe becoming colder, darker, and lonelier as expansion pulls everything apart beyond hope of reconnection. But this future is unimaginably far away, tens or hundreds of billions of years. And for now, the void is simply a region emptier than average, not the final state of the universe, but a preview of what much of space will eventually become as expansion continues to dominate over gravity's pull. In the nearer future, thousands or millions of years from now, the void will look essentially unchanged because cosmic evolution happens slowly, and even the universe's expansion is gentle on timescales we can comprehend, producing changes that require billions of years to become noticeable. The galaxies in the void will continue to evolve, forming stars slowly, occasionally experiencing supernovae and aging gradually, but their isolation will remain, and they will continue to be lonely outposts in a vast empty region, shaped by their unusual environment throughout their existence. So the void's future is more emptiness, more isolation, more growth as expansion pulls everything apart, and this future teaches us that the universe is not static, that structure is temporary, and that emptiness is perhaps the ultimate fate of all regions as cosmic evolution proceeds. The void serves as a preview of cosmic destiny, showing us what awaits the entire universe as dark energy drives accelerating expansion, and in its current emptiness we see the future loneliness that will eventually characterize all space when galaxies drift beyond each other's horizons and isolation becomes universal. This perspective is both humbling and profound, revealing that the richness we see today is temporary, that the cosmic web will eventually unravel as expansion pulls it apart, and that the void's current state represents not an aberration but the eventual norm, the destiny toward which all structure slowly moves. Yet even in this far future, the void will not be without interest, because within each isolated galaxy, stars will still form for a time, planets will still orbit, and perhaps life will still exist, unaware of the vast emptiness surrounding it, living in islands of light separated by distances so vast that the rest of the universe might as well not exist. The evolution of voids over cosmic time can be measured by comparing nearby voids to distant ones, because distant voids show us the past, how voids looked billions of years ago, and comparing them to nearby voids reveals how emptiness increases, how expansion affects void properties, and how the cosmic web's structure changes as the universe ages. These measurements help astronomers understand dark energy's history, whether its strength has remained constant or changed over time, and how it will behave in the future, and voids provide one of the best ways to study these questions, because their properties are particularly sensitive to dark energy's influence across cosmic time. The future of the void is intimately connected to the future of everything, because what happens in the void will eventually happen everywhere, and studying the void's evolution helps us understand not just this one region, but the ultimate fate of all structure, all galaxies, and perhaps all life in a universe dominated by accelerating expansion. Imagine a civilization arising on a planet in a void galaxy, living in one of those 60 lonely islands scattered through the Boötes Void, and consider how different their perspective would be, how their understanding of the universe would develop, and what challenges they would face in discovering cosmic structure. From their world, the night sky would be remarkably empty, showing only the stars of their own galaxy, perhaps one or two faint smudges representing the nearest void galaxies tens of millions of light years away, and beyond that, nothing, just darkness stretching in all directions without any visible structure. Their astronomers would see this emptiness and might initially conclude the universe consists only of their galaxy, that beyond their stars lies infinite empty space, and that they are alone in the cosmos, the only island of matter in an otherwise empty universe. This perspective would shape their philosophy, their cosmology, their sense of place, and discovering that they are wrong, that the universe is actually full of galaxies, but they live in an unusually empty region, would be a profound revelation, transforming their understanding completely. To discover the cosmic web from within the void would require powerful telescopes, capable of detecting faint, distant galaxies beyond the void's edges, and patient surveys that map the sky carefully, looking for the faint light of structures far away. And this discovery would take time, dedication, and advanced technology. Eventually, with sufficient effort, they would detect distant galaxies, realizing that structure exists beyond their empty neighborhood, and further observations would reveal filaments, clusters, and the cosmic webs pattern, showing them that their isolation is unusual, that most of the universe is more crowded, and that they happen to inhabit an exceptional region. This discovery would change everything, replacing their lonely universe with one full of structure, and they would realize that studying their own region's emptiness could teach them about cosmic structure formation, about dark energy, and about how the universe organizes matter on the largest scales. They might study their own void carefully, measuring its properties, mapping the few galaxies within it, and using this information to understand cosmology, and they would appreciate their unique perspective, realizing that living in emptiness provides insights that civilizations in dense regions might miss. Their sense of cosmic loneliness would be profound, knowing that the nearest significant structures are hundreds of millions of light years away, far beyond any hope of travel or communication with current technology, and that their galaxy is truly isolated in a way that galaxies in richer regions are not. But this loneliness might also be peaceful. No threat of collision with neighboring galaxies, no crowding, no gravitational disturbances, just their galaxy evolving quietly in vast empty space, free from external influences, and this isolation might be seen as a gift rather than a curse. Philosophically, they might develop unique perspectives on existence, shaped by living in emptiness, appreciating solitude, understanding isolation on cosmic scales, and perhaps developing a cosmology that emphasizes the rarity of matter, the preciousness of structure, and the vast empty spaces that separate islands of existence. Their art, their literature, their culture would all be shaped by growing up under an empty sky, and encountering a civilization from a void would give us unique insights into how environment shapes thought, how location influences perspective, and how different our universe would seem from their vantage point. Astronomers study the Boötes Void using galaxy surveys, carefully mapping the positions and distances of galaxies across large regions of sky And when they applied these techniques to the Boötes region, they discovered the void, finding far fewer galaxies than expected in a large volume of space. These surveys involve measuring redshifts, the stretching of light caused by expansion, and redshift tells us distance, allowing astronomers to create three-dimensional maps of galaxy distributions. And these maps revealed the void's structure, its size, and its remarkable emptiness. Modern surveys use large telescopes and sensitive instruments to detect faint galaxies, pushing deeper into space, finding more of the void's sparse galaxy population, and refining our understanding of its properties, its galaxy content, and how it compares to simulations and theoretical predictions. The Sloan Digital Sky Survey and similar projects have mapped millions of galaxies, creating detailed three-dimensional maps of cosmic structure. And these maps show the cosmic web clearly, with voids like Boötes standing out as underdense regions within the larger pattern of filaments and clusters. Studying voids requires patience and careful analysis, because the few galaxies they contain are often faint, requiring long exposure times to detect, and distinguishing true voids from regions that are simply undersampled requires comparing observations to expectations based on the average galaxy density in the universe. Astronomers also study how void properties vary with distance, which means studying voids at different cosmic ages, and this tells us how voids evolve over time, whether they grow, how their galaxy content changes, and whether their properties match predictions from models of structure formation and dark energy. Future observations will improve our understanding significantly. New telescopes and surveys will find fainter galaxies, map larger volumes, and detect more voids. And this data will refine our measurements of dark energy, test cosmological models, and help us understand the universe's structure and evolution more completely. The James Webb Space Telescope and upcoming surveys will be particularly valuable, detecting faint distant galaxies that previous instruments missed. And these observations will tell us whether voids are truly as empty as they appear, or whether they contain many faint galaxies we have not yet detected. Observing voids is challenging because, by definition, they contain few bright objects. But this challenge makes the observations valuable, pushing our instruments and techniques to their limits, and teaching us about the faintest, most distant structures that are hardest to detect but crucial for understanding cosmic structure. Some mysteries about voids remain unsolved, including whether they are completely empty or contain dark matter and gas even without visible galaxies, how exactly they form and evolve, and whether their properties match all predictions from our cosmological models, or reveal surprises that require refining our theories. These mysteries drive ongoing research, with astronomers continuing to study voids carefully, mapping them, measuring their properties, and comparing observations to simulations. And each new survey brings us closer to understanding these vast, empty regions and what they teach us about the universe. So observing the void is an active area of research, not a finished story, but an ongoing exploration. And as technology improves and surveys expand, our understanding of voids will deepen, revealing more about cosmic structure and the forces shaping it. Their early astronomers might catalogue their own galaxy's stars exhaustively, believing that this was the extent of the universe, and their cosmology might focus on their galaxy's origin and fate, never imagining that beyond their local region lies a universe teeming with billions of other galaxies arranged in vast cosmic patterns. The moment of discovering the first external galaxy would be momentous, proving they are not alone, but initially they might think it an exception, a single other galaxy in an otherwise empty cosmos, and only with continued observation would they realize that faint smudges scattered across their sky represent dozens of galaxies, all part of their void. Eventually discovering the cosmic web beyond the void would be their Copernican moment, realizing their location is not typical, that they inhabit an unusual region, and that the universe's normal state is far richer in structure. And this discovery would fundamentally alter their understanding of their place in the cosmos. Of course, this is all speculation. We have no evidence of life in void galaxies or anywhere beyond Earth, but the thought experiment is valuable, helping us appreciate how much our cosmic perspective depends on where we live, and how different the universe would seem from different locations within it. We are fortunate to live in a relatively rich region where galaxies are abundant, where structure is visible, and where we can see the cosmic web relatively easily, allowing us to develop accurate cosmology without facing the challenges a void civilization would encounter. Their scientific journey would be our journey reversed, discovering first their isolation, then gradually learning that beyond it lies richness, while we discovered first our rich neighborhood, then gradually learned that vast voids separate the structures we see, and both perspectives illuminate different aspects of cosmic reality. In imagining life in a void galaxy, we expand our understanding of perspective itself, recognizing that truth depends partly on viewpoint, and that a civilization in the void would develop cosmology differently, arriving at the same ultimate understanding through a very different path, shaped by the emptiness that surrounds them. The techniques used to study voids have evolved dramatically since the 1980s, when Robert Kirshner discovered Boötes, and modern surveys can detect galaxies much fainter than those early observations, allowing astronomers to probe voids more deeply and understand their properties with greater precision. Spectroscopy plays a crucial role in void studies because measuring a galaxy's spectrum reveals its redshift, which tells us its distance, and building up thousands or millions of such measurements creates the three-dimensional maps that reveal voids as underdense regions in the cosmic web structure. Radio observations add another dimension to void studies, because radio telescopes can detect neutral hydrogen gas that may exist in voids even without forming galaxies. And studying this gas helps astronomers understand whether voids are truly empty or contain matter that simply hasn't formed visible structures. Some voids may contain diffuse gas, dark matter, and even dark galaxies, objects so faint they escape detection, and future observations with more sensitive instruments will reveal whether voids are truly as empty as they appear, or whether they contain hidden matter we haven't yet learned to detect. The search for void galaxies requires dedicated effort, because these objects are faint and scattered, and finding them requires surveying large areas of sky to sufficient depth. And each new void galaxy discovered adds to our understanding of how galaxies form and evolve in such isolated environments. Comparing void galaxies to galaxies in dense regions reveals how environment shapes evolution. And these comparisons show that void galaxies are often bluer, actively forming stars, and less disturbed by interactions, properties that tell us about the role of environment in shaping the galaxy population we observe. The study of voids has become increasingly sophisticated, with astronomers using statistical techniques to characterize void properties, compare them to simulations, and extract cosmological information. And this sophisticated analysis turns voids from mere curiosities into powerful tools for understanding fundamental physics. Void catalogues now contain hundreds of identified voids, each one measured and characterized, and these catalogues allow astronomers to study void populations statistically, looking for patterns that reveal how voids form, how they evolve, and what they tell us about the universe's composition and fate. Machine learning and artificial intelligence are now being applied to void studies, helping astronomers identify voids in large data sets, classify them by properties, and compare them to simulations more efficiently. And these new techniques are accelerating our understanding of void properties and their cosmological implications. The future of void observation lies in next-generation surveys, massive projects that will map billions of galaxies across vast volumes of space, revealing voids in unprecedented detail. And these surveys will transform our understanding, potentially revealing new types of voids or unexpected properties that challenge our current models. As observations continue and technology advances, our picture of voids becomes richer, more detailed, and more nuanced, revealing that these regions are not simply empty but complex structures with their own properties, histories, and roles in the cosmic web. And each observation brings us closer to fully understanding these vast, lonely regions. We return now to Earth, to our rich neighborhood, having explored the Boötes Void in imagination, and we can appreciate how fortunate we are to live where we do, in a region where galaxies are abundant and the universe's structure is visible and accessible to our telescopes and theories. The Milky Way sits in a relatively dense region, part of the local group of galaxies, which itself lies on the outskirts of the Virgo supercluster. And this location gives us a view of many galaxies, many structures, making it easier to discover the cosmic web and understand our place within it. If we lived in the Boötes Void, our perspective would be profoundly different. The night sky would be empty, and discovering cosmic structure would require far more advanced technology, and our cosmology would develop differently, shaped by the isolation and emptiness that surrounds void galaxies. But we do not live there, we live in richness, and contemplating the void helps us appreciate this richness, understanding that our abundant view of galaxies is not universal, that much of the universe is emptier, and that we are fortunate to inhabit a region that reveals so much. The Boötes Void teaches us that emptiness is natural, that voids are normal features of cosmic structure, and that most of the universe's volume is actually empty, with matter concentrated in relatively small regions along filaments and in clusters, while voids dominate the space between. This structure is beautiful in its organization. The cosmic web of matter and emptiness, creating a pattern that extends across the entire observable universe. And voids are as much a part of this pattern as the dense regions, defining the spaces between structure and completing the picture of how matter is distributed on the largest scales. Emptiness has its own kind of beauty, a simplicity, a quietness. And contemplating voids can be meditative, peaceful, reminding us that not everything needs to be filled, that space can exist without content, and that distance and isolation have their own profound qualities worth contemplating. The loneliness of the void is not sad, but peaceful, a cosmic solitude that is complete, absolute, and in its own way perfect, showing us that the universe has room for emptiness, that not every region is crowded, and that isolation on cosmic scales creates a different kind of beauty than the rich clusters we usually study. The void represents a kind of cosmic minimalism, where less truly is more, where the absence of structure creates its own presence, and contemplating this emptiness helps us appreciate both what is there and what is not, finding meaning in the spaces between matter as much as in matter itself. In a universe that seems obsessed with complexity, with galaxies and stars and planets and perhaps life, the void offers simplicity, a region where almost nothing happens, where change is slow and emptiness reigns, and this simplicity has its own appeal, its own power to calm and center us. As you drift towards sleep tonight, let the image of the void settle. Vast, empty space, dark and quiet, stretching for hundreds of millions of light years, and find peace in this emptiness, letting it calm your mind as you rest, knowing that somewhere far away, this loneliest place exists, waiting quietly in the darkness. The void reminds us that the universe is vast beyond comprehension. That distance has meaning, that space is real, and that between the islands of matter lie oceans of emptiness that are just as much a part of the cosmos as the galaxies themselves, completing the picture of what the universe truly is. We have explored the Boötes Void together tonight, from its discovery to its properties, from imagining journeys through it to contemplating life within it. The journey through cosmic emptiness has been a journey through scale and perspective, teaching us about distances so vast they defy imagination, about isolation so profound it transforms meaning, and about the universe's capacity to create both richness and emptiness, both crowding and solitude, both complexity and the purest simplicity. We have learned that voids are not aberrations but natural features, that they teach us about cosmology, about structure formation, about dark energy and dark matter, and that studying emptiness reveals truths about the universe that studying fullness alone could never show us. The void has shown us that location matters profoundly, that where you are in the universe shapes what you can see and understand, and that our perspective from Earth, rich in galaxies and structure, is a gift that allows us to comprehend cosmic architecture more easily than civilizations in emptier regions ever could. It has reminded us that time scales matter too, that cosmic processes unfold over billions of years, that what seems permanent is temporary, and that the void's current emptiness is both a record of the past and a preview of the future, when much of space will be as lonely as Boötes is now. Most importantly, perhaps, the void has taught us that emptiness is not nothing, that absence has presence, that silence speaks, and that the spaces between things are as important as the things themselves, creating the structure, the pattern, the rhythm that makes the cosmos comprehensible and beautiful. In contemplating the loneliest place in the universe, we have found not fear, but peace, not anxiety, but calm. And this transformation reflects a deeper truth, that understanding brings comfort, that knowledge dispels fear, and that even the vastest cosmic emptiness becomes approachable, even friendly, when we take time to understand it. The Boötes Void will always be there, 700 million light-years away, existing in its profound isolation, slowly growing as the universe expands and continuing its role as both a natural feature of cosmic structure and a reminder that space has room, vast room, for emptiness and solitude and the peaceful darkness between the stars. Thank you for traveling with me tonight through the Boötes Void, exploring its emptiness, its isolation, and its role in cosmic structure, and I hope you found something calming, something fascinating, or simply a moment of peace in contemplating this vast region of almost nothing. Until next time, rest well, let the stars watch over you, and remember that emptiness has its own beauty, that vast distances can be peaceful, and that the loneliest place in the universe is also one of the most serene, perfect for drifting through in imagination as you fall asleep. Good night, and may your dreams carry you through quiet, empty spaces, where distance reigns, where darkness is complete, and where the universe shows its capacity for creating vast, peaceful regions that exist simply to be empty, to demonstrate that not everything needs to be filled, and that sometimes the most beautiful thing is nothing at all. The pure emptiness that balances all the matter and energy and complexity we see. The void that completes the cosmic pattern and makes the universe whole.